SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 23. We have been discussing about the ways to represent ordered and unordered samples with respect to combinations and permutations. Today we are going to sort of continue that and see if we can mention or we can arrive at a distribution which can actually be helpful in estimating probability. The estimation of the probability was done in respect of acceptance sampling. So let us say in a particular case we are inspecting about n pieces, and we may search for defects or non-conformances in n pieces and record the total number of such defects. This is measuring quality by count of defects. In inspecting or testing n pieces, we may consider whether each of n pieces does contain any defects. Each piece having one or more defects is called a defective. This measure is known as the count of defective. So we will consistently use the following symbols. N is the number of units in a sample, D let us say is the number of defective units in sample units n, and therefore the probability of having a defective, which is also the fraction defective, is D by n. So it is basically sort of indicative of a proportion of the defective units in the sample, and obviously the number of good units as a proportion are 1 minus p or 1 minus D by n. So therefore exactly there are n minus d units which are good as respect to the total sample size, which is n. So that is the fraction of good pieces, 1 minus p, and then obviously the number of defective units in a sample can be represented as n times of this fraction probability. So obviously d has been defined in a manner so that d equal to np. So suppose we had a process, so we are going to sort of see and evaluate if this so called binomial distribution, which I am just going to bring in the next slide, is somehow useful in the process of estimation of all these probabilities given this particular situation of selecting d defectives from n. Supposing we had a process with population fraction defective of 0.1, that means about 10 out of 100 samples are acceptable, and for a sample size of 4 there could be, if we look at let us say a draw size of 4 from this overall n population size, there can be either a case where all the samples are good samples, so you have 0 defective, or you have at least one of the samples out of the 4 draws which is defective, 2 of the samples again which are defective, 3 in defective, and all 4 are defective. So these are some of the possibilities which will happen when we are drawing samples from an otherwise large population of n total samples. So how do we write the probability of drawing all good pieces? So obviously this probability can be defined as just because the fraction defective is 0.10, therefore the amount of good pieces or the fraction of good pieces is actually 90%. So there are about 90 items in that 100 lot which are actually good samples, and so the probability of d being 0, now the d being the number of defects being 0, is basically that all the 4 items that are drawn are good items. So therefore we can just simply, because they are independent of each other, these draws are not dependent on each other, so we can say that 0.9 to the power of 4 is what the total probability of 0 defective would be, which is 0.6561. So thus about 2/3 of the time, about 66% of the time, we draw a sample of n equal to 4 pieces from the process where all 4 will be good samples, probably provided there are about 10% defectives in a particular sample. Now let us seek a probability of the second case, which is 3 good and 1 defective. That means in 3 draws you have good samples and in 1 draw you have defective sample. So what are the basic combinations of when this defective can occur? So you have 4 different draws, so the defective can occur in the 4th draw or the 3rd draw or the 2nd draw or the 1st draw. Okay. So you have a probability of getting one order which is good in the 1st draw, good in the 2nd draw, good in the 3rd draw, and bad in the 4th draw, represented by D. Okay. Similarly you can have the defective drawn in the 3rd draw, So, the first two are good and the last one is good again. The defective drawn in the second draw, where the first and the last two are good samples, and then one in the first draw and the remaining 3 in the last 3 draws are good samples. So, you can actually again represent this as the probability of getting good times probability of getting bad. Obviously, the acceptance rate is 90%, so 10% are defectives. So, you can say the probability of getting 3 good samples in a succession followed by a defective is 0.9 into 0.9 into 0.9 times of 0.1, and similarly the all variation that is happening here is in terms of where this 0.1 is placed. So, you can see this is in the third place, the second place, the first place, so on and so forth. And so, basically you can represent all this as 4 times of 0.9 to the power of 3 times of 0.1, which is actually represented as 0.2916. So, it is basically 4 times of 0.9 to the power of 3 times of 0.1. Okay. So, we consider next the samples with where 2 of these 4 draws have defective samples. So, how many such combinations will exist? You will have 2 good, 2 defectives. You can have 1 good, 1 defective, again another good, another defective. You can have 1 good, 2 defectives followed by a good. You can have a defective, then a good, then a defective, then a good, or 2 defectives at the beginning and 2 goods at the end, or otherwise you can also have 2 defectives at the 0th and the 4th, or the first and the 4th draw, and second and third draw being good samples. So, these are all what is needed for getting exactly 2 defectives in the successive 4 draws that you are making from the sample n. So, obviously we can actually now put these outcomes together again as 6 times of 0.9 square, that is the probability of having a good sample, times of 0.1 square, which is the probability of having a defective sample, which is 0.0486. We can do the same thing for d equal to 3, that means the defectives, number of defectives now are 3 out of the 4 draws. So, you can have 4 times of again the same, as you had 3 good and 1 defective, the only thing here would change, which basically is going to be if it is 3 defectives. Similarly, for the d equal to 3, which is basically number of defectives equal to 3 and number of good 1, there are only 4 orders of sampling results, where the p probability of having 3 defectives d equal to 3 is given by 4 times of 1 good, that is 0.9 to the power of 1, times of 3 defectives 0.1 to the power of 3 in an identical manner as before. So, this comes out to be about 0.0036. Finally, for d equal to 4, all 4 must be defective. So, you have 0.1 to the power of 4 defining 0.0001 as probability of having d equal to 4 defectives. So, if we summarize all these data points together about the probability of having either 0 defectives or 3 good and 1 defectives, and also 2 good and 2 defectives, or let us say probability of having 3 defectives in the 4 draws or all 4 as defectives, the summation, which will come out to be also representing the total probability or probability of drawing four samples from the sample of from the population of size n as all 4 being good, which is probability of getting exactly d equal to 0, plus 3 defective, 3 goods and 1 defective, which is actually 0.2196, plus again the possibility of getting 2 defectives, which is 0.486, plus the possibility of getting 3 defectives, which is 0.0036, plus the possibility of getting all defectives or 4 defectives. So, there are actually 5 terms which are there, and if I just correlate all this and write in terms of these powers, this is 0.9 to the power of 4, this is actually 4 times of as you can see here, 0.9 to the power of 3 times of 0.1 to the power of 1, plus this actually represents 6 times of 0.9 to the power of 2 times 0.1 to the power of 2, plus 3 times of 4 times of 0.9 to the power of 1, 0.1 to the power of 3, plus again 0.1 to the power of 4. So in general this can be recorded as a case where this 4 is actually 4C1, this can be 4C2, this is 4C3, and this one can be 4C4, where C depicts the combinations as talked earlier. So I am going to sort of represent all this together as a distribution, where I can say that the total probability in this case of the whole draw to happen is basically 0.9 to the power of 4 plus 4C1, 0.9 to the power of 3, 0.1 to the power of 1 plus 4C2, 0.9 to the power of 2, 0.1 to the power of 2 plus 4C3, 0.9 to the power of 1, 0.1 to the power of 3 plus 4C4, 0.1 to the power of 4. In other words, this can be represented as a probability distribution of the number of good samples plus the number of bad samples to the power of 4. Okay. So this is actually nothing but the binomial distribution, and each term of this distribution is representing something. For example, this term represents the probability of having 3 goods and 1 defective, this represents 2 goods and 2 defective, this represents 1 good and 3 defective, and similarly this represents all the 4 defective. So that is how you represent the total probability in this binomial distribution, and generally you can write a generic term of representing D defectives is basically PD given as C4D, 0.9 to the power of 4 minus D, 0.1 to the power of D. This is also a representative of the dth term of the binomial distribution of n equal to 4, and the p equal to 0.9 and q equal to 0.1. In general, the PD becomes equal to C n D, p dash to the power of n minus D, q dash to the power of D, where p dash is the probability of having defective sample D by n, for example in this particular case, and q is 1 minus p dash, which is the probability of having a good sample. So that is how you represent through the binomial distribution the whole acceptance sampling mode, and also can estimate the number of defects in a particular sample in a certain subsequent draw which comes up. So this is one important case which has been described here. So just because we are talking about binomial distribution, I think it is very important and prudent for us to know about what really is a binomial distribution and what are some of the characteristic properties of this distribution. So particularly where many sets of trials are made of an event with a constant probability of occurrence p, the expected average number of occurrences in the long run is obviously n times of p, and so np is the expected value or the mathematical expectation, where this mathematical expectation has been a concept probably taught in earlier first and second year level courses, and mathematical expectation of x, where x equal to 0 if an item is acceptable, or x equal to 1 if it is rejectable. Okay, so we distribute it in a manner. So the mathematical expectation is an operator which is expressed as followed. So the mean of x, where x is basically again this 0 if an item is acceptable or 1 if it is rejectable, that is how you have placed the function. So mu of x is basically defined if x is continuous as integral x fx dx, x varying between minus infinity to plus infinity, and in case of discrete distributions, in fact this binomial distribution that you are talking about is a discrete distribution, you can define it as xpx, sigma x varying between 1 and n. And so basically we will apply the second formulation to sort of calculate the mathematical expectation. So in the interest of time we will close this particular module, but in the next module we are going to bring up two different formulation strategies, where in one we will calculate what is the mean of a binomial distribution using this definition here of the in case of discretized x of a mathematical expectation or mean of the distribution, and then also calculate or try to calculate the standard deviation of such a discretized distribution, so that we are enabled now to maybe based on that estimate things like number of defectives or even number of units which are actually defective, so on and so forth in a particular acceptance sampling plan. So thank you so much for this particular module.